Okay, good evening. Tonight's lesson is in 10.8. This is we did skip a section. We'll be coming back to it. The lesson is about power theorems. That means nothing to you at the moment, so I'm going to just say a little bit in a way of introduction. We've spent quite a bit of time talking about arc measures and angle measures. So, for example, in the chord situation, we have talked about how it is the relationship between angle measure and arc measure, and so we've done a lot with the measures of angles and arcs. Tonight's lesson we're going to be looking actually at segment length. That is, what do we know about the length here and this length? Or if I have a secant tangent situation here, what do I know about this length here and the secant lengths and the chords Y and W, for example? So this is where we're going tonight. Okay, we've been here in the past, so you can expect a few more theorems, 3 to be exact. So we'll start in with the first theorem, Theorem 95. Again, in your pink booklets, you should be recording these. This is called the chord-chord power theorem. So immediately be thinking, what is a chord-chord? What are we talking about here? If two chords of a circle intersect, it is important that you're able to digest the statement. If two chords of a circle intersect inside the circle. So what is that going to look like? Okay, imagine it. Is this what you were imagining? Hope so. Alright, then what is the case? We're going to look at some distances here. Again, distance we're looking at is AB. We're looking at this distance is AB. This distance here is BD, 2.73. That's the distance. Looking at CB, this distance, and EB, which is that distance. Okay, so we're looking at those distances there. Is that too faint for you? If so, let me get that a little different color there. Inductively, we're going to take a look at the product of this length times this length. And I get, when I take EB times CB, I get 13.56. And lo and behold, when I multiply these two segments, I get 13.56. Now, is that just lucky? Was I lucky with this example? Let's play with it. I just changed them. Notice that the products are still equal. Let's play with it again. In fact, we can see that they are always equal. This segment times this segment is going to equal the product of these two segments. Kind of a nice deal. Kind of curious as to why that works. Again, the reason why we study circles is they're very predictable because they're very simple. So, let's finish the then statement. So, if I've got a chord, complete this. If two chords of a circle intersect inside the circle, then the product of the measures of the segments of one chord is equal to the product of the measures of the segments of the other chord. Again, you will find this written out on page 493. Okay. So if you need to write that down, pause your video. If not, we're going to look right directly at an example. Let's move to an example and kind of, well, actually, let me pause before I go to the example. And let's hide these things, and let's think a little bit about deductive. I hope that you have gotten a sense and appreciation in this class about some nice conclusions that mathematics brings, and the simple beauty of an auxiliary. There is a simple auxiliary, two simple auxiliaries that make this proof very clear. And those are these, oops, these auxiliaries right here, A to C and E to D. Why is that the case? Let's take a look at what that brings. Just by putting those two simple auxiliaries in, we can see that this arc is shared by this inscribed angle and this inscribed angle. And we see that this shared arc is shared by this inscribed angle and that inscribed angle, therefore they must be congruent. And by vertical angles, we know that those are congruent. And so what we have here is a set of similar triangles. Triangle ABC is similar to triangle EBD. Immediately, once we have triangle similarity, where do we go with this? Set up your proportions. AB over EB is equal to BC over BD, which is equal to AC over ED. Now, using this fact, I'm going to ignore this one here. Not really interested in that one. Look at this proportion. What falls out of this? BC times EB equals AB times BD. That's beautiful. Let's move on to the next example. We're gonna apply this right away here. So example number 1. Solve for x. So I've got 2. This value is 2. This value is 3. This value, I'm sorry, that value is 6. This value is 3. And that is x. Alright? So, let's apply. 3 times x equals 2 times 6. Solve for x. That distance is 4. Pretty nice. Pretty simple. Okay, let's look at the next theorem, Theorem 96. This is a tangent-secant power theorem. Again, it's going to be talking about distances. Tangent-secant, so be thinking about what this picture looks like even before I put it on. If a tangent segment and a secant segment are drawn from an external point to a circle. So picture a circle, an external point, and then a tangent and a secant created. This is what you've got. Okay, is that what you were thinking about? Now, what do we have here? Let's take a look at our distances. A couple of distances that I want to draw your attention to. The first one is the secant segment. That is the entire distance here. The secant segment is this right here, what I've highlighted. The entire distance. That is set apart and different from this distance here, which is the exterior secant segment. And then we have the tangent segment, which is this, tangent segment. So there are 3 parts of this figure that we want to understand its distances. We want to understand the entire secant segment length. Then we will look at the exterior secant segment. And finally, the tangent segment. Now check out these calculations. If I multiply the secant segment, that's everything, and I multiply this entire secant segment by just the external, I get 89.29. And then if I multiply the tangent segment by itself, I square it, I get 89.29. And you can see that that is always going to be the case. You can adjust this. You can see that this value and this value, that product is the same always. So let me put some markings on this. What am I multiplying? I'm multiplying this distance times this distance to equal this distance times this distance again, or squared. Okay, so look at the picture. Is that something that you can internalize? All right. Now, again, following the inductive approach, let us think about this deductively. All right. Again, a few nice auxiliaries make this very, very possible. What do you think those auxiliaries are? These auxiliaries right here, and that might not be intuitive, but I want to show you why. If I draw these two auxiliaries in, this is what I have. Notice this arc is intercepted by this inscribed angle, and that same arc is intercepted by this tangent chord angle. So those are congruent. Furthermore, angle C is congruent to itself. So I have got two triangles. Do you see two similar triangles here? I got two triangles that are congruent. Let's record them. I've got, not congruent, I'm sorry, similar. I've got triangle A, C, D. That's A, C, D. Must be similar to triangle D, C, B. I see that D and A are congruent, C and C are congruent. That leaves D and B congruent. Again, what falls out of a similarity statement like this but your similarity ratios. Furthermore, what falls out of this but our rule? So AC over DC, we're going to keep this one here. Let's see, CD over CB, AD over DB is not, this guy is not the one that we're all interested in. So this, that proportion right there allows me to say, by cross multiplication, AC times CB is equal to CD times DC. Now, with a little bit of a closer eye, we see this. What is CD? CD times DC is the tangent. Is the tangent guy squared. What is AC? AC is the secant distance. And what is CB? That is the external. That is a deductive proof for this theorem. Again, if I'm moving too fast, always pause and rewind. Let's look at an example. Example 2. Let's put it. Let's put some numbers to it. AD is 16. That's 16 here. AC. That's the entire distance here. AC is 18, and BC is, I don't know. What is BC? We'll call that X. Okay. Well, let's use my rule. I know that X squared. Let's review here the rule. I need to take the entire secant, multiply it by the external, and that should equal the tangent multiplied by itself. Okay? So let's do that. Do I know what DC is? I do. It's 18 take away 6. That's 16. That's got to be 2. So my entire secant is 18. My external is 2. And that equals my x squared. Okay? What is 18 times 2? 36 equals x squared. Solve this. X equals plus or minus 6. The negative value doesn't make sense, so x must equal 6. BC must equal 6. Okay? Alright. Let's move on to now the third and final theorem. It's called the secant-secant power theorem. Alright, try to imagine what this looks like without me drawing it. If two secant segments are drawn from an external point. Okay, so I've got a circle and I've got an external point and two secants. Let's see if you can imagine this figure. If you did, you're correct. Let's look at some distances here. Here are the distances that I'm interested in. The blue secant segment, that would be the entire secant segment. The blue external is just this, let me highlight it, just this external part. Okay, that's the blue external. Then we have the entire black secant segment, and just like before, we have the external, black external segment. So I've tried to color coordinate it for you. Okay. What you're going to see a similar calculation using multiplication. Okay. If I take the blue external, that's this, and multiply it by, blue external is this, and multiply it by the entire secant, I get 63.72. If I multiply the external, the black external, times the entire secant, I get 63.72. I get the same value. Let me mark on the diagram. That is to say, if I multiply the entire secant times the external, I will get the same value as if I multiply the entire secant of the other one multiplied by its external. Okay, so we have all of these theorems have the same flavor. Let's finish writing this one. I think I forgot to do that on the last one. You'll have to get that in your book written out here. So, if two secant segments are drawn from an external point, then again the product, we're multiplying, of the measures of one secant segment and its external part is equal to the product of the measures of the other secant and its external part. Okay, so you can see that there. In short, you could write it this way: total secant times external equals total secant times external. Now, I'm going to leave the proof for you to figure out. for extra credit. I'll give you extra credit if you can prove this one. Use my hints from the past. Two auxiliaries make it come together. So try to do that. I'll give you extra credit if you do so. Let's look at an example. Put this into context here. Put some numbers on it. So I've got FH is 16. I've got FH, that is this distance here, is 16. Fi is 3. GE is 8. Find FGX. Alright. Well, my formula is the total times exterior equals total times exterior. Alright, well, 16 is the total secant, and its external is 3, and the total secant length from F to E is what? X plus 8. And the external is x. So now you can see here we're going to have some quadratics creep in here. Okay? So this is 48 equals x squared plus 8x, and we have a quadratic to solve. Set it equal to 0. X squared plus 8x minus 48 equals 0. And then we can factor. So we can expect some factoring to come back into play here. 48 is minus plus 12 x minus 4. Gives you negative 48. Very good. Okay, and so now what's my answers? Sorry, here we're going to go up to the top. So either x equals negative 12 or x equals positive 4. Well, since this is geometric, it's got to be positive value. We found x must be 4, fg must be 4. Okay, so with that, I'll kind of close the lesson, and you can expect to apply those three theorems in upcoming problems.